Hello everyone! So we are going to do the 3 slides that we skipped over calorimetry, and those were specifically over bomb calorimetry. So I think this was slide 45, 46, and 47. So those are the slides that I want to do first, and then we're going to finish up the PowerPoint by doing slides 52 through the end. So I'm going to make this in 2 separate videos just because I want to do bomb calorimetry separate, and then we'll do the enthalpy of reactions or enthalpy of formations for the other video. So in terms of bomb calorimetry, so we talked about a coffee cup calorimeter. And a coffee cup calorimeter, we had the 2 styrofoam coffee cups, and then we would add water, and we have some type of reaction that's happening in the water. And so in our coffee cup calorimeter, I could measure the temperature of that water, because if the water increased, then I know that the system is releasing energy, so it's giving energy to the water, which would cause that thermometer to go up. That would make my temperature increase. If my system is giving energy to the water, so my reaction is giving energy to the water, or my temperature is increasing, I would, the water temperature is increasing, I would consider that then a release of energy by the system, so that would make my Q, or delta H value, a negative, right? Because if the system is releasing energy or giving energy away, then that would make it a negative, so that would be an exothermic reaction. If the temperature decreases, if I see a drop in temperature, that would mean that the system needed to absorb energy from the water, which would then mean that my delta H or Q value would be positive, and that would make it an endothermic reaction. So just to kind of review those signs and those terms, just to make sure that we're on the same page. Okay, so with a bomb calorimeter, we can have reactions that can be carried out in a sealed, what we call a bomb, such as this little contraption right here. Pretty much a bomb calorimeter will work the same way, but mostly we study, in terms of bomb calorimetry, we're studying combustion reactions. So combustion reactions are what we usually study in terms of bomb calorimetry, and we're pretty accurate in measuring the change in enthalpy using a bomb calorimeter. So what happens, or how this works, we have a substance that's going to be placed in a small cup, and then that small cup is going to be placed within an insulated sealed vessel, and that insulated sealed container is what we call the bomb. So here's my little small cup that has my sample, and then we're going to place that small cup inside kind of a bigger cup, but it's an insulated container, and that's what's going to be called our bomb. So the bomb is made to withstand very, very, very high pressures. And this bomb has an inlet valve for adding oxygen or other types of like electrical leads. And that may just be so that way I can change different things about the calorimeter itself. So I have my bomb, so I have my bomb, my reaction chamber. So my sample's here. I've placed that sample in my reaction chamber in this bomb, and then I'm going to place that bomb inside a bigger insulated container. So we have like all of these containers within containers. So I have my sample, I have my bomb, my reaction chamber, and then I have my big insulated container overall. Now, the combustion reaction is started off, or I can initiate the combustion by passing some type of electrical current through a wire that's in contact with the sample. So I see here that I have these 2 wires here. So I see them sticking out of my insulated container. If I look inside that insulated container, I would see that they're also within that bomb. And I can look that I have these 2 little wires that are attached here, or they're touching that sample. So if I use these sample ignition wires, so if I take these 2 wires and I initiate some type of combustion, I'm going to get that combustion reaction happening in the bomb or in the reaction chamber. When that wire becomes hot enough That's when we get the combustion reaction to happen. All of that heat that will be released when the combustion occurs will be absorbed by the water, because a combustion reaction, we know, will definitely release heat. So in this, I'm going to get a bunch of heat that will be generated or be given off from that system to the water, to the surroundings. So I can measure that heat based on also that temperature change, or I can see that based on that temperature change. So I'll see the temperature rising. We used something similar. We used in our lab a similar equation, with the same one that we'll use here for the bomb calorimetry, and that is, oh, well, apparently, oh, there it is. Okay, and that is, our Q reaction for a bomb calorimeter will be Ccal times my change in temperature. So I have my Q, which we know is the same thing as delta H, right? And that's going to be equal to Ccal, which is just a constant. Typically, this constant will be given to you. So when we did our lab, we had to find that constant. And we did that for our styrofoam cups in the lab. So in part A of our lab, we found that Ccal. And then our change in temperature. And that will give us our Q, or our heat flow. So let's do, I want to do an example with this. Here's our example. So I have the combustion of methylhydrazine, which is CH6N2, which is a liquid rocket fuel, produces into gas, CO2 gas, and liquid water. When 4 grams of methylhydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter will increase from 25 degrees Celsius to 39.5 degrees Celsius. In a separate experiment, we found that the heat capacity for the calorimeter, which is Ccal, this heat capacity for the calorimeter is 7.794 kilojoules per degree Celsius. I want us to calculate the heat of reaction, so I want to find delta H for the combustion of a mole of CH6N2, or methylhydrazine. Okay, so I'm going to go off of this to get onto the Promethean board, so make sure you keep this problem out in front of you so that way you have that as a reference. Okay, so I know that methylhydrazine was being combusted. So let me just write out the reaction that we have. We have CH6N2 was liquid, and that combusts. So that means it's reacting with oxygen in the air. So it's going to react with oxygen to produce, and it told me what it was producing. It said we're going to produce nitrogen gas, so we're going to produce N2 gas. We're also going to produce carbon dioxide gas. And then liquid water. Okay, but I need to make sure that this is all balanced, so 2 here, do a 5 in front of that oxygen, and then should be 2, 2, 6. Okay, so there's my balanced reaction for the combustion of methylhydrazine. Okay, so I want to find, ultimately, delta H. That's my goal. And I know delta H is equal to Q. And I know that for a bomb calorimeter, Q is equal to a negative Ccal times change in temperature. Well, I know that Ccal, in this case, they told us that. They said that that heat capacity for the calorimeter was measured to be 7.749, I think it was kilojoules? Yeah, kilojoules per degree Celsius. So I know Ccal, so let's just go ahead and plug that in. And still I have that negative, so let's bring the negative. So negative 7.749 kilojoules per degree Celsius. And then I want to take that and multiply it by the change in temperature, which our change in temperature should be final minus initial. we initially started off at 25 degrees Celsius, and then our final was 39.5 degrees Celsius. So our change in temperature should be 39.5 minus 25, which would be 14.5 degrees Celsius. So let's plug that in for our change in temperature. 14.5 degrees Celsius. So now if I just multiply these together, I'm going to get my Q value to be a negative 113, and that should be kilojoules. Because we're already in kilojoules, and my degrees Celsius would cancel out. So Q would be a negative 113 kilojoules. But they asked me to calculate the heat of the reaction for the combustion of a mole of CH6N2. And so this is just kilojoules, but I don't have it per mole yet. Well, in the problem, it said, let's assume we have 4 grams of this methylhydrazine. That's how much we combusted in the bomb calorimeter. So if I want to get moles, I need to convert that 4 grams of methylhydrazine, which is 4 grams CH6N2. I need to convert that to moles. So I'm going to use molar mass here. And if I found the molar mass, it would end up being 46.1. So if I take 4 and divide that 4 by 46.1, that would give me 0.0868 moles of CH6N2. So now I have moles, and I also know that Q was negative 113 kilojoules. So to find that overall kilojoule per mole, that delta H, I'm going to take my Q, divide it by the number of moles. So delta H will equal a negative 113 kilojoules over my number of moles here, which is 0.0868 moles. So if I do that, that should give me we'll say a negative 1.30 times 10 to the third kilojoules per mole, and that's of CH6N2. So this problem is pretty much the same as when we do like Q equals MCAT. We have, except for in our calorimeter, we have Q equals a negative CCal times our change in temperature. Now, in that equation, they have that negative that's already associated there. So let's think about this. If our change in temperature will increase, then my final minus my initial will be a positive value. So Q would be negative. And when our temperature is increasing, it's because the system is releasing energy. So our delta H value should be negative. So that should make sense because that system is releasing energy, so that negative indicates that. So that looks good to us. And if our temperature, let's say our temperature decreased, and our final was smaller than our initial, our final was lower than our initial, that would make this change in temperature negative, which would make my Q overall positive, and that would represent an endothermic reaction, and that positive sign would represent that endothermic reaction. So the signs definitely work out here for us. So we did our Q, we found our number of moles, so then that way we could find our kilojoules per mole, or our joules per mole if they ask us for it in that. So we could do Q equals MCAT, we could do Q is equal to the negative CCal times delta T, and it will be very specific, guys, too, when they ask you pretty much, I think, which one you should be using. So when we say a bomb calorimeter, we'll be using this Q equals the negative CCal times delta T. If it's not a bomb calorimeter, we'll be using our Q equals MCAT. Okay, I think the last slide here for bomb calorimetry. So because the volume in the bomb calorimeter is constant, we really aren't measuring delta H. So because our volume is staying the same, what we're really measuring is our change in internal energy instead of not necessarily our change in enthalpy. And that's because remember that the change in enthalpy we know that that's heat flow, but if we think about first law of thermodynamics, we said that change in enthalpy was equal to change in internal energy and then that pressure volume work. But if the volume stays constant, then I don't have a change in volume, so that work kind of goes away. So then my change in enthalpy would be just equivalent to my change in internal energy. So for most reactions, the difference, though, between our change in internal energy and change in enthalpy is so small that it really doesn't matter. So we say that we're measuring delta H, or we can say that we're measuring change in enthalpy. We're really measuring change in internal energy, but the difference between these two is so small that it's negligible. So we just kind of think, whatever. We're really saying we're measuring this too. Okay, so those are our slides for bomb calorimetry. Now I'm gonna start a different video, starting off with enthalpies of formation, and that's going to be slide number 52. So let's go ahead and get our slide ready for this one, and then you can go ahead and get ready for your next video.